This video is the first of 2 videos on the ideal gas law. The last video was about gas pressure. So the main points in this section are going to be the relationships between pressure and temperature, volume and temperature, pressure and volume and the number of moles. So in the last section, we talked about gas pressure, and that's one of the important macroscopic physical properties, meaning we, macroscopic sized people, can physically measure that property, the pressure. And the units we use for pressure can be atmospheres, pascals, millimeters of mercury, or others. But pressure isn't the only macroscopic property that we care about, nor is it the only one we can measure. There are a few others, including volume, which has units of liters or cubic meters, temperature, which we always use the units of Kelvin, and the number of moles, which tells us about how many molecules there are. And of course, that unit is moles. So these are the other important variables that we are going to measure. And so now we need to look at the relationship between each of these two in order to understand how one affects the other. So we'll start with pressure and temperature. So pressure and temperature have been studied for a long time, back in the 1700s, by a man named Guillaume Amonton and another man named Joseph Louis Gay-Lussac. Gay-Lussac was the one who nailed it down to being a precise relationship quantitatively. So before I tell you what it is, let's see if we can figure out each of these relationships using an example. So to relate pressure and temperature, let's talk about a bike tire. Because I take my bike to school, and it is very important to me what the pressure of my bike tire is. So this part is the tire, and this part is the tube around the outside here, and that's the part with the air in it. So let's assume for now that there's a constant volume, and let's say that I filled it last week in September, and it's at a certain pressure. So what is going to happen to my tire if I don't fill it until December? In December, the temperature outside is lower. So what's going to happen to that bike tire? The bike tire is going to be flat. It's going to be difficult for me to bike on that. So the pressure is going to be low. So we'll make a plot over here, and we'll put pressure versus temperature in Kelvin, cross my heart. So we have low temperature and low pressure. Okay, let's think about it the other way. What if my tire that I just filled wasn't filled again until summer? So July or August, when it's super hot outside. In August, the temperature is really high. What happens to my bike tire? The gas inside is going to heat up, and the pressure of the tire is going to increase. So much so that I'll have to be careful that my bike tire doesn't explode when the weather gets too warm. So we've got high temperature, high pressure for that point. And we can see the relationship between these two is positive. There's a positive slope on the line that connects them. That means that they are directly proportional. Pressure and temperature are directly proportional at constant volume, which is important. We are only changing 2 variables at a time here. Okay, So pressure and temperature are directly proportional. And another way that we can write this is to write it more like an equation. So we can say pressure equals temperature times some number, some constant K1. If you multiply by the constant, those numbers are equal. And you can see that they're directly proportional because they're both on the numerator on opposite sides of the equal sign. And if we rearrange this to put the constant on one side by itself, we have the constant equals pressure divided by temperature. And so here, pressure and temperature are on the same side of the equal sign, one on the top and one on the bottom. They are still directly proportional. If you increase one, you have to increase the other for this constant to remain constant. So that's the relationship between pressure and temperature, directly proportional. So let's move on to volume and temperature. And there was a famous balloonist named Jacques Charles, and he was the one who was really interested in the relationship of temperature and volume, because when you take a hot air balloon way up into the atmosphere, it gets very, very cold up there. And you really want to know how the volume is going to change so you know if you're going to drop and hit the ground or not. So here's a balloon. It's not a hot air balloon, but we're not going to push my drawing skills today. So let's say that I blew up this balloon and then I put that balloon in the freezer, somewhere where it's cold. What's going to happen to that balloon? The colder the balloon gets, the more the balloon is going to shrink. Not to scale, obviously, but it will be smaller. So if the temperature goes down, the volume of the balloon is also going to go down. So we'll go to our plot here, volume versus temperature in Kelvin, cross my heart, and we've got low temperature, low volume. Okay, let's take that same balloon, let's warm it up again. So let's take it out and let's put it somewhere with a high temperature. Take it out on a nice hot July, August day, and we'll put it in the sun and we'll let it sit there. That balloon is going to swell up and it's going to become even larger. So your volume is going to increase. High temperature, high volume. High temperature, high volume. There we are. So we have got a positive linear relationship once again. So we've got volume is equal to temperature times a constant. And I'm just going to call this one K2 just so that it doesn't have the same letter, the same name as the last one, because the constants are different for each. And we can rearrange that to volume over temperature equals K2. And this is all happening at constant pressure. Okay, so we've talked about the relationship between pressure and temperature. Those are directly proportional. And the relationship between volume and temperature, those are directly proportional. But I don't want you to think that all variables are directly proportional. It's not true for all of them. So let's talk about something that isn't directly proportional. Pressure and volume. Pressure and volume were investigated by Robert Boyle in the 1600s. Lots of good gas law studies going on in the 1600s. So to think about the relationship between pressure and volume, let's think about breathing and what happens in your lungs. Anyone who has said drawing lungs is easy has not seen me drawing, but we will give it a go. Okay, so each of you has two lungs, and they're kind of wiggly looking, roughly triangular looking things. And there's a big muscle underneath them. So these are supposed to be lungs. And the muscle underneath is called the diaphragm. And the diaphragm changes the volume of your lungs. So here's the volume of one of these kind of sad looking lungs at this point. So when you want to breathe in, what happens? Your lungs need to get bigger, right? You take a big, deep breath in, you have big, large lungs. So let's say your lungs get much bigger. So the diaphragm is going to move down, pulls the lungs to have a larger volume. So the volume is going to increase. Here's the diaphragm now down here. And when that volume increases, that's going to change the pressure inside your lungs. The pressure inside the lungs is now going to be slightly smaller than the pressure outside the lungs. And that means that air is going to rush in to fill that void. So when the volume increases, the pressure decreases. So we've got pressure on the Y, volume on the X, high volume, low pressure. The point is going to be right around here. Okay. Let's try the other way. I'll have to draw it on a separate line. Okay, so here's lungs. Some wiggly triangles. There's my diaphragm. This is the volume I've got in one lung. Okay, so let's say we're going to be breathing out. When you breathe out, your diaphragm pushes this way. It squeezes those lungs so that they're smaller. There it is. The diaphragm is pushing. We have made the volume smaller. And when the volume is smaller, all the gas molecules are stuck, shoved together, and the pressure gets higher. And when the pressure is higher, it's higher than outside, so air goes out of your lungs. And so that means we have low volume, high pressure, point up here. And in this case, it's more of a curve than a line. So the relationship between these two variables is inversely proportional in this case because there's a negatively sloped line. So pressure is going to be some constant times 1 over volume this time. Or if we rearrange it, P times V equals K3. And this is true at constant temperature. We always have a constant variable. All right, and then one more thing we want to change is scientists really like their data to be linearized or in a straight linear line. And so we have several tricks up our sleeve to change the data to make it look more linear. And one thing we can do is if we have a relationship in the form of an equation, we can use those variables as they are as the axes to give us a linear relationship. So if I change my plot to be P on the y-axis and 1 over V on the x-axis, that is going to give me a linear relationship. As 1 over volume increases, the pressure increases as well. So you might see this graph drawn this way, so it looks more like a line. Okay, so that was pressure and volume for our breathing example. And our final variables to look at are volume and the number of moles, N. And this was studied by our favorite mole guy, Amadeo Avogadro, father of Avogadro's number, or the number of things in 1 mole. And our example here is going to be a pool float, something we might have used a month ago when it was a little bit warmer. So when you want to lay on one of these little pool floaties, one of these mattresses inside the pool, we want to add as much air as possible so that it's nice and comfy and so that it actually floats on the water. So if we blow it up more and we add more moles of air, the volume is going to be larger than it was over here when it was only medium inflated. So the more you blow into it, the more the volume increases. So we've got volume on the Y, and on the X, high number of moles, high volume. If you have an annoying little brother, of which I have one, you might catch him trying to let some of the air out of your mattress. It'd be funny. He might let some of the moles of gas out, causing the volume to decrease as well. So it's not very comfy, and it might even sink when you try and sit on it. So low moles, low volume, and we have a line connecting those as well. So number of moles and volume are directly proportional. So we can write that equation as the volume equals number of moles times some constant. And this one is at constant pressure and temperature. This is all happening in the same pool on the same day. And we can rearrange that to be constant equals volume over number of moles. So that's the relationship between pressure and volume and number of moles, volume and temperature, and pressure and temperature. And in the next video, we'll put all of those relationships together to form the ideal gas law.